about a few more heat calculations that are a little bit more involved. Here's the problem. We've talked about specific heat is for temperature changes. We've talked about melting and boiling using heat of fusion, melting and freezing using heat of fusion, and boiling and condensing using heat of vaporization. But would you agree that sometimes more than one of those happens at a given heating session? Okay, so let's say we start with ice that's actually not at zero yet. It first has to heat up, then it can start melting. So because of that, sometimes we have multi-step problems, and these are going to be some examples where you're going to have more than one step. And I call them heating curve calculations because we're going to use a heating curve to actually see what we have to calculate, okay? Now, it's very important to know, usually these problems are going to involve water, because water is our most common substance that can be found as a solid, liquid, or gas at a given reasonable temperature range, whereas the others have much weirder, wilder temperatures. We just don't see their phases as often. So we're usually dealing with water. Be careful because we're not always, but usually we're dealing with water. And you do need to know, it's in your reference table too if you don't remember, but you definitely need to know that the melting point of water is 0 degrees Celsius and the boiling point of water is 100 degrees Celsius. If you don't remember those numbers, they're in your reference table, but you're really just better off knowing those numbers. 0 degrees Celsius is the melting point, 100 degrees Celsius is the boiling point. We have to read these problems. We have to ask ourselves, I see that there's a temperature change, but is there also a phase change in between there? So technically, every time you're given a temperature change, before you just dive right in and use specific heat, you have to think, was there a phase change during this temperature change as well? So I'm going to read you an example that would include that, and then we'll work through it together. I'm actually going to work through 2 of them because these are a little bit trickier. Once you get them, it's going to be a lot of points that you'll get correct on the test, which is awesome. But we got to get to that point first. So here we go. How much heat is required? First of all, that gives us a hint that this answer is going to be positive. To heat 15.8 grams of water from 30 to 122. Initially, you would read this and you would say, this is a specific heat problem because this temperature is changing. But what happens to water at 100 degrees Celsius? Water boils, right? Here, water would be a liquid, but here, water would be a gas. So let's draw a little miniature heating curve here. And I want you guys to actually see what's happening. Okay, here's a heating curve of water. It starts as a solid, then it melts, then it liquid, then it boils, then it's a gas. So if we're starting at 30, that's going to be, and I'm going to grab another marker for this. If we start at 30, that's going to be like right here. And if we end where it's a liquid, and if we end at 122, that's right here. And that's where it's a gas. So everywhere there's a change in the line, that is a new problem we have to use. The first one we're going to have to do is go from heating up the liquid up to 100. So this is 100. That's the first thing we have to do. Then we have to boil the liquid. Then we have to heat up the liquid from 100 up to 122. So this is actually a 3-step process. And I'm going to show you how we need to set it up. And I'm going to tell you, if for each setup, you're going to get points. If you just simply do a temperature change on this, you're going to lose more than just 1 point for an incorrect answer. You're going to lose a point for each step that you did not include in your calculations. So you need to make sure that you get these right, because they are going to be a lot of points. If you get them right, a lot of points you got. If you don't get them right, it's a lot of points to lose. So let's look at here. What I want you to do is label off to the side exactly what we're doing. The first thing is we're going to have to heat up that liquid from 30 degrees Celsius to 100. That's going to be one problem. Then we're going to have to boil that liquid, go from a liquid to a gas. Then the last step would be to go from 100 degrees Celsius to 122 degrees Celsius. So at this point, we have to figure out what we got to do. Specific heat here, because it's changing temperature. So that would be mass times specific heat times the change in temperature. This one is boiling, so it is mass times delta H of vaporization. And this last one is a temperature change again, MC delta T. But be careful, this right here is a gas. So we're not going to use 4.18 here. We're going to use the 2.02 for the specific heat of gas, of water vapor. Do make sure that you are showing your units in your work, okay? Just like I've been expecting from you all semester. So here we go. Now it's just going to be a matter of plugging it in. But let me ask you, if we're trying to find the heat from here all the way to here, we're trying to find this total heat, all of that, okay? What do you think we're going to have to do to these three numbers when we find them? When we find the amount of heat needed to raise the temperature of the liquid, the amount of heat needed to boil, the amount of heat needed to raise the temperature of the gas. If you look, here's the first one from here to here, here's the second one from here to here, and here's the third. What do you think we're going to do to all three of these reactions? We're going to add them. We're going to add them up. We're going to sum them. And whatever they add up to, that is our total heat. One more question. We saw that this, before we dive in and start doing the problem, we saw that it says required. That means our total answer is going to be positive. Let me ask you, does that mean all three steps are going to be positive? Let me ask you this. Are we going to have to heat it up and continually heat it up? Or are we going to heat it up and put it in the fridge, then heat it up and put it in the fridge? No, in order to heat up something from a liquid to a gas, we're going to have to continually add heat. So on all of these problems that are multi-step, they're either going to be all positive or all negative. You're never going to have one step that's positive, one step that's negative. They're either all going to be positive or all going to be negative. And in this case, they're all positive. Okay, so let's just dive right in. The first one's going to be MC delta T. The mass is 15.8 grams. The specific heat of water, and it is a liquid at this point, so we can use the 4.18 joules per gram degrees Celsius. And the change in temperature, we're going from 30 to 70, so that is a 70 there. Oh, should have my unit. Always include your units in your work. Okay, let's do the next one. This would be mass times the delta H of vaporization for water. That is 15.8 grams times our 2260 joules per gram. And notice the grams cancel out. We end up with joules. We're looking for heat, so that's definitely correct. Okay, let's do the last one. Now we're changing the temperature, so this is a specific heat problem. Times, but we're no longer using 4.18. We're now using the specific heat of a gas, because after it reaches 100, it's definitely a gas now. That would be 2.02 joules per gram degrees Celsius, and times the change in temperature. It's going from 122 to 100, so that is 22 degrees Celsius. I have to see this. I have to see exactly what you're doing off to the side, which step of the heating curve are we at, and then I have to see you plugging in the numbers. Now at this point, we're going to add all three of these. I don't need to see an individual answer for each. If you want to put that all in your calculator at once, I'm okay with that. I would advise you put it in your calculator at least one time if this is the test or the quiz, because it's really easy to make a mistake. But I don't need to see individual answers. I would rather you not round more than once. I would rather you just round one time at the end. What I want you to do now is I want you actually to practice putting this in your calculator. If you want to write the answers off to the side, I think it allows you to make fewer mistakes. I really do. You can definitely do that. But I want you to pause the video at this time to make sure that you have time to put this in your calculator, because I don't want anyone to miss this question because of a calculator error. I will be going over the correct answer, but I want to make sure that you can get that in your calculator. So here is the correct answer. It is 41,033 joules. But let's talk about significant figures here. I'm going to give you a special gift with this, okay? When you look back at the original problem, we have 3 sig figs, 2 sig figs, and 3 sig figs. Now, technically what you should do is follow the sig fig rules for each individual step as you're multiplying. So this one would have 2, this one would have 3, this one would have 2. But do that, and then each time you add, then you're looking at the placement of the numbers. So who knows how many sig figs you'd have at the end. Instead, I'm giving you a gift here. I'm letting you look back at the original problem and go with the smallest sig figs. So since this problem only has 2 sig figs at the smallest, our final answer would need to have 2 significant figures. So instead of writing 41,033, I'm going to write 41,000. There's the 2 significant figures right there. Now what I will tell you is that I do always write in my key not only this answer, but I do always write the correct number of sig figs based on doing each step. So if you really want to take the time to do that, you can, and I would accept it. I always have 2 possible sig fig answers, the actual correct way and the easier way. The reason why I'm giving you a freebie on this, you will still have a point for the sig figs, but the reason why I'm making it a little easier is because I feel like this problem is hard enough. I don't want you to focus too much on the significant figures. We are going to do one more problem because this is pretty complicated, so we're going to work through one more. How much heat is released when 21.2 grams of water cools from 13.7 degrees Celsius to negative 24.8 degrees Celsius? And to give myself a little bit of space, I'm going to go ahead and erase this little bit that I've already done in this previous problem. So the first thing you need to do is when you see this temperature change, you need to think, is there a phase change? When water is at negative 24.8, what state of matter is it? It's a solid. When water is at 113, what state of matter is that? A gas. Oh, so when we're looking at our heating curve, so there's a simple heating curve for any substance. We've got solid, liquid, gas. Would you agree that we're starting here and we're ending up here? Every time the line changes direction, that's going to be a step. First, we're going to have to heat the solid. Then we're going to have to melt the solid. We're going to have to heat the liquid. Then we're going to have to boil the liquid. And lastly, we're going to have to heat the gas. So this is actually a 5-step process. This is the longest you're going to have. Okay? So the first thing is we're going to have to go now. Oh, you see how this says released? That tells us that this answer is going to be negative. That means all 5 steps have to be negative. I do think this makes it a little bit trickier putting in your calculator, so when you're dealing with negative numbers, make sure that you're doing that correct in your calculator. You're doing that correctly. Okay, so the first step is that we are starting with 113.7, okay? So the first step would be, we have to cool that down. We have to cool that down to 100 degrees Celsius. Then it will be able to condense. So then we're going to go from a gas to a liquid. Then we're going to have to cool the liquid from 100 degrees Celsius. See, right now we are here. We're cooling the liquid down from the boiling point to the melting point. Got to be 100 degrees Celsius down to 0 degrees Celsius. Then we can melt the substance. So then we can go from a liquid to a solid. Oops. And at that point, we're at 0 degrees Celsius, but we have to end with negative 24. So the last step would be to go from 0 degrees Celsius down to negative 24.8 degrees Celsius. So I will go ahead and write my equations down so we can see what we're doing. Notice all 5 of these should be negative. So this one we're going to have to do specific heat because it's a temperature change. This one's going to be heat of vaporization because it's boiling, or in this case, condensing. This is going to be specific heat again, but we're talking about a liquid. This one's going to be heat of fusion because we're melting it. Actually, in this case, I keep saying it wrong. We're freezing it. So it's going to be negative. And in this case, we're looking at specific heat because it is a solid losing temperature, going down in temperature. Okay, now it's just a pretty long, involved plug and chug. Okay, we do want to double check that all 5 of these are negative. So the first is mass, 21.2 grams, times specific heat of a gas is our 2.02. And when we take final temperature minus initial temperature, that's where we get our negative 13.7 degrees Celsius. Ooh, and I'm not doing a good job writing my units. Make sure you always write your units. Okay, the next one is going to be the heat of vaporization. So the heat of vaporization of water is that 2260, but since we're condensing, it needs to be negative. In order to condense a gas, you have to take away heat. So it's going to be 21.2 grams times a negative 2260 joules per gram. Then we have a temperature change, but now we are dealing with liquid water, so it's going to be 4.18. 21.2 grams times the specific heat of liquid water, 4.18 joules per gram degrees Celsius, times the change in temperature. We're going from 100 to 0. So our final is 0. Our initial is 100. That's going to be 0 minus 100. That's where we get the negative 100 degrees Celsius. Then we have liquid to solid. It's going to lose energy because it's freezing, it's losing heat, but now we're going to use the heat of fusion. That would be 21.2 grams times 334, negative 334 joules per gram. And last but definitely not least, we are going to go from a solid at 0 to a solid at negative 24.8. Final minus initial, negative 24.8 minus 0 is a negative 24.8. So it's going to be 21.2 grams times, that's where we use the 2.05. Please double check you're using the correct specific heat. Sometimes my students just automatically write 4.18 without even thinking. Make sure you're using the correct specific heat. When we're at a solid, it's not going to be the 4.18 joules per gram degrees Celsius times negative 24.8. Okay, again, I want you to pause the video to put this in your calculators because I don't want anyone to miss this on the quiz or test because you make a calculator mistake. Practice, practice, practice. So I will be going over the correct answer, but I first want to make sure that you can do it yourself. So when you get this in your calculator, you should get, you have to add this all up, but keep in mind, every step is negative, so watch those negative numbers. You should get negative 65,519 joules. Well, let's go back. Remember, you can write down each one and figure out the sig figs for each and then add it and go to the placement, but I'm okay with you cheating and going back to the initial problem, and your answer should be the fewest sig figs, 3, 4, and 3. So our final answer should have 3. That's going to be this 5. Does the 1 round up the 5? So it's negative 65,500 joules. And there is your answer. That is the amount of heat released when you take a gas at 113.7 degrees Celsius and you cool it all the way down to negative 24.8. That's a lot of heat. So thank you for watching about heating curve calculations. Practice, practice, practice.